friends, today we will continue our discussion on interaction of radiation with matter. In the last class we have seen there are three different processes occurs when radiation falls on a matter, right? And we have understood all the three processes qualitatively. Today we will start to do some quantitative analysis of those three processes. This was first done by Einstein, hence there are some coefficients involved which are known as Einstein coefficients. What are the three different processes? Okay, the first one is absorption. So in this case we have seen that the transition occurs from ground state to excited state. That is, this is a type of transition in which atom in the ground state moves to the excited state, and this transition occurs through absorption of radiation, that is photon. Okay. The second one is spontaneous emission. In this case the transition occurs from excited state to ground state, and during this transition photons are emitted, right? And this transition occurs naturally without any external stimulation. So we have seen that this is the ground state, this is the excited state. So when a photon falls on this atom will move to the excited state, right? And this is what? Absorption. And after some time this will come down automatically to the ground state by emitting a photon, and this is what? Spontaneous emission. Now coming to the third one, that is stimulated emission. In this case the transition from the excited state to the ground state is triggered by external radiation or stimulations. This is also an emission, right? That means the atom is moving from excited state to ground state, but the difference between these two is that the spontaneous emission occurs without any external stimulation, whereas this stimulated emission that is triggered by some external radiation or stimulation. So in this case what happens when the atom is in the excited state? If some photon triggers this excited atom, it will come back to the ground state by emitting some photon, and this photon both are in same phase, right? So this is what we have seen in previous video. Today we will do some quantitative analysis on these three processes. First, let us understand what is rate of absorption. So this is the ground state E1 and this is the excited state with energy E2, and we all know that E2 is greater than E1. Today I will be introducing one more quantity, that is population. So the population of atoms in state 1, that is in the ground state, let us consider that as N1. What is the meaning of population of atoms? That means how many atoms are present in the ground state, that is considered as population of atoms in state 1, and I have taken this as N1. Similarly, the atoms which are present in state E2 or the second state, that is represented as N2. So the population of atoms in state 2 is equals to N2. In stable state what happens? Generally all atoms they try to be in the ground state, and hence we are having N1 is greater than N2. This is the normal equilibrium condition. In case of absorption we have seen that this is the atom. When a photon is hitting this atom, by absorbing this photon this atom will move to the excited state, that is E2. This is what? Absorption, right? Now what is this rate of absorption? So the rate of absorption is the rate of decay of number of atoms at energy state 1, that is the ground state, per unit time. When atom is moving from ground state to higher energy state. That means there is decay of atom at ground state. So the rate of decay of number of atoms at energy state A1. So how many numbers of atoms are getting decayed per unit time? That is what the rate of absorption. So the rate of absorption is equals to minus dN1 by dt. So this is the rate of change of atoms in ground state. This negative sign here shows that the number of atoms in the ground state is decreasing with respect to time because of absorption. So initially if there are 5 atoms and one is moving to the energy state 2, we are left with 4 atoms. So it decreased from 5 to 4. That means the number of atoms in the ground state is decreasing, and hence it is minus dN1 by dt. Now what are the quantities on which this rate of absorption depends? The rate of absorption depends on two quantities. First one is, it is proportional to the number of atoms in that particular state. Here it is moving from state 1, so I have taken it as N1. So how many number of atoms are there? Depending on that, if more numbers will be there, more will move to the higher state. That means it is directly proportional to the number of atoms in that particular state, that is N1. So it is minus dN1 by dt is proportional to N1. Further, this absorption takes place whenever we are incidenting some radiation or photon on the metal. So if we will incident more number of photons, then the probability of transition from ground state to higher state will increase. That means it is directly proportional to the density of photons having frequency nu12 and energy h nu12. That is also we can call as the energy density. What is the density of the radiation we are incidenting on the metal? Frequency nu12, I am writing this because we are considering two states. One is at energy E1 and E2. So this difference is h nu12. So I am writing nu12 is the frequency which corresponds to the energy between or energy difference between E2 and E1. So it is nu12. So this rate of absorption is directly proportional to E nu12. This is the frequency which corresponds to this energy difference. So if I will consider this as equation 1, this as equation 2, combining these two equations, I can write minus dN1 by dt is directly proportional to N1 E h nu12, right? So this is the equation. So if I remove this proportionality sign over here, then I have to multiply this quantity with a constant factor, right? So I can write minus dN1 by dt is equals to B12, this is the proportionality constant, N1 E h nu1 2. And this proportionality constant is known as Einstein coefficient of induced absorption. Now coming to the second type of interaction, that is spontaneous emission. So what is the rate of spontaneous emission? In case of spontaneous emission, what happens? We are having two energy states, and now we are considering the atom at the excited state. Okay, so once this atom has moved from this ground state to this excited state, it will stay here for a particular time interval which is known as the lifetime of this atom. After that time is over, this will come automatically to the ground state, and while this transition is occurring, this atom is moving from excited state to ground state, it will emit radiation of energy h nu, and this nu is nothing but nu12, what we have considered just in the before slide, right? So the rate of spontaneous emission is the rate of decay of number of atoms at energy state 2, that is the excited state, per unit time due to spontaneous emission. Here I am mentioning spontaneous emission because we are having two types of emission. One is spontaneous and the second one is stimulated, right? So this rate what we are calculating here, this is for spontaneous emission. So whatever transitions are due to spontaneous emission, we will consider only those emissions. So here the rate of spontaneous emission is the rate of decay, because again when this atom is moving from E2 to E1, there is decay of atoms at the energy state E2. So it is decay of number of atoms at energy state 2 per unit time, and that too due to spontaneous emission. So the rate, how can I write? The rate of spontaneous emission is equals to minus dN2 by dt, and here I am writing this is because of spontaneous emission. Here also this minus sign indicates that there is decay of atoms with respect to time. So can you tell me what are the physical quantities on which this rate depends? For absorption we have seen that depends on the population at ground state, and also that depends on the photon density. But here this transition occurs without any external trigger, okay? It is occurring by its own. So it depends only on the number of atoms present at the excited state. So this rate of spontaneous emission is directly proportional to the number of atoms in state 2, that is the excited state. So I can write minus dN2 by dt, this represents, this is the spontaneous emission is directly proportional to N2. Here it is independent of the photon density because it is not affected by the photon density. Once the atom is moved to the excited state, it will remain there for the lifetime, and once that lifetime is completed, it will come down automatically to the ground state. So it is not at all depending on the photon density, only it depends on the population at energy state 2. If more number of atoms will be there, then per unit time more number of transition will occur. If less number of atoms are there, then we will be getting less number of transitions or spontaneous emissions, right? So now if I will remove this proportionality sign, I have to multiply with some proportionality constant, and it is written as A21, and this A21 is known as Einstein coefficient of spontaneous emission. Now coming to the third one, that is stimulated emission. Just to recall what happens in case of stimulated emission, here these are the two energy states, E2 is greater than E1, and if the atom is at the excited state, if it is triggered by a radiation or photon before the expiration of or before the completion of lifetime, it will come back to the ground state, and while coming back it will emit some radiation. Thus in case of stimulated emission, if some photon triggers this atom which is in the excited state, this atom will come back to the ground state, and while coming back to the ground state it will emit some radiation h nu, right? Further these two photons, they will move together. So this is what occurs in case of a stimulated emission. So I can write that the rate of stimulated emission is the rate of decay of number of atoms at energy state 2, that is the excited state, per unit time due to stimulated emission. Here also the number of atoms are getting decayed from the excited state, but this occurs due to stimulated emission. So I can write the rate of stimulated emission is equals to minus dN2 by dt, and here I am writing this is because of stimulated emission. Previous one is due to spontaneous emission, that's what I had written there SP. Here I am writing this as ST to indicate that this is because of stimulated emission. Now the next task is we have to find out what are the physical quantity on which this rate depends on. Here again the rate of stimulated emission depends on two quantities. The first one is number of atoms in the excited state E2, that is N2, because the transition is from excited state. So if more number of atoms are there in the excited state, then we will be getting more number of emissions, right? So it is directly proportional to the number of atoms in state 2, that is N2. Thus from here I can write minus dN2 by dt, this represents stimulated emission, is directly proportional to N2. N2 is the population at the excited state. Further, we have seen that this stimulated emission occurs due to the incident radiation, and hence if the density of the incident radiation is more, then we will be getting more stimulated emission, right? So the stimulated emission is directly proportional to the density of photons having frequency nu12 or energy h nu12, or that is nothing but the energy density. So I can write this as minus dN2 by dt, stimulated emission, is directly proportional to E nu12. If we are incidenting more energy, then we will be getting more number of transitions, right? So combining these two, I can write minus dN2 by dt, that is stimulated emission is directly proportional to N2 and E nu12. Okay, so if I will remove this proportionality sign, I have to multiply this with a constant. So I can write minus dN2 by dt, stimulated emission, is equals to B21 N2 E nu12. Here this B21 is known as Einstein coefficient of stimulated emission. So these are the three rates of different types of transitions occurring in case of interaction of radiation with matter. While explaining these three rates, we have used three different Einstein coefficients, right? Let me summarize those three coefficients what we have used. B12, it is the Einstein coefficient of induced absorption. The second one is A21, that is Einstein coefficient of spontaneous emission, and the third one is B21, which is nothing but Einstein coefficient of stimulated emission. So these are three Einstein coefficients. These are also known as Einstein's A and B coefficients. Let us see what are these letters indicating. Okay, first B12, if you will see, this transition is from state 1 to state 2 because this is a absorption. In case of absorption, the transition is from state 1 to state 2, right? So it is written 1 to 2. It is moving from 1 to 2. Now coming to these two, here you can see it is 2 to 1. Okay, 2 to 1. So the transitions are from state 2 to state 1. So whatever suffix we are using, if it is 1 to, that means the transition is from 1 to 2. If it is 2 1, that means the transition is from state 2 to state 1. Now coming to the letters used over here, that is A and B. A is transition occurs by its own. This is the case for spontaneous emission. If you recall, this spontaneous emission doesn't require any trigger. Here we are not supposed to incident any radiation. This occurs by its own. Once the lifetime is over, that atom which is in the excited state, that will come down automatically to the ground state. So here this letter A is used when the transition occurs by its own. But considering this other two where the letter is B, in that case this is induced absorption. We are using a photon, right? Similarly, if you will see the stimulated emission, here also you need a outside trigger, that is some radiations to be incident on the matter to initiate this stimulated emission. So this letter B is used when the transitions are induced by external radiational photon. So these are the notations used by Einstein to define the three rates for three different processes which occurs whenever radiations interact with matter. Today we will stop here. In the next class we will derive some equations which relates all these three Einstein coefficients. Thank you all. If you like the content of the video, please press the like button and share the link with your friends. And also do subscribe to my channel to get the notifications whenever I am uploading a new video. Thank you all.